gosh, bug. I can hear Bug's stomach. Yeah, I can hear your stomach. It's really loud. It's really, really loud. Eat something. He has an upset stomach. I can hear it, and he's refusing to eat. I can hear. It stinks very badly. All right, I'm going to start. I don't think everyone's here, but I'm starting anyways. So what we are going to be talking about today is Gauss's law for systems with cylindrical symmetry. Okay, so let's remember if a system has cylindrical symmetry, it has an axis. Okay, so it has an axis of symmetry that extends from minus infinity to plus infinity, and if we rotate the system about that axis, it's the same charge distribution. If we take, because it's an infinite cylinder, if we take it and we shift it up or we shift it down, again, it's the same charge distribution. Okay. So yeah, we typically would draw the axis of the cylinder. So there's the axis of the cylinder. And in cylindrically symmetric systems, the electric field points directly away from the axis. Okay, so meaning that if this is the axis, or it could point directly towards the axis, it's going to be directly away like so. That's the electric field. All right. So this would be a positively charged system. If we wanted to draw this in more of a 3D view, so there's 3D view, and we've got electric field that goes like this. So it kind of is going out in all directions. Like so. Okay. So plus infinity to minus infinity, plus infinity to minus infinity. So in this case, our Gaussian surface now Hazel's coming in, and so Bug's breakfast is sitting in front of him, and it's funny. I'll put here's Bug's paws. No. Here's Bug's paws, and I'll put his breakfast in between his paws, right up next to his face, and then he'll go like this and turn away from his breakfast. He's so dramatic. He's driving me nuts. So the Gaussian surface is a cylinder. Okay? So if we were to look at that from this 3D perspective, it's going to look like this. So here's our Gaussian cylinder. Kind of like that. And if we were to look at it from its side, you take a toilet paper roll. So our Gaussian surface is basically a toilet paper roll. And you look at the toilet paper roll from the side, it just looks like a rectangle. Okay? So here is our... Are these people even teaching right now? I'm getting like text messages from other teachers. It's like, what the heck's going on? We're in the middle of class. So the radius of that Gaussian cylinder is r, and the length of the Gaussian surface is L. So what do we get if we evaluate the flux through that that Gaussian surface? Well, a cylinder has three faces. It has its middle face, it has the left face, and the right face. So we have E left dot A left. Okay. We have E right dot A right. And we have E middle dot A middle. Okay, now if we look at the left and the right faces, well, the left and the right faces have area vectors that point away. So the area vector points away from the face, okay? But the electric field, we can see, points up and down. So both the left and the right faces have an angle of 90 degrees between the area vector and the electric field. And the dot product we know involves cosine of theta, and so the cosine of 90 degrees is 0. Okay? So what that means is that these two terms drop out. Now, what about the middle face? Well, the middle face is this curved face, and it has an area vector that points away from the middle face. So here's our area vector, and then the electric field points in the same direction. Okay? So that means that this middle face has an angle of 0. Now, if the angle between two vectors is 0, then the dot product is simply the product of their magnitudes, E times A. So what is the area of that middle face? It's the surface area of the middle part of the cylinder. And the middle part of a cylinder is a circle which has a circumference of 2 pi r extended along the length of the cylinder. So the surface area is 2 pi r L. Okay? So if we go to the full Gauss's law, okay, what we get is the full Gauss's law is the integral of E dot dA is equal to charge enclosed by the Gaussian surface divided by epsilon naught. And so we know that the left-hand side is E times 2 pi RL, and then the right side is charge enclosed for epsilon naught. Then divide both sides by 2 pi RL, and what we get is that the electric field is charge enclosed divided by 2 pi epsilon naught L R. Okay, so this is the formula for today. All right, and so basically what we're doing is we're just figuring out what is the charge enclosed. So just like for the last lesson, I'm going to do 2 examples. And this first example is going to take a little while to draw. So it's a cylindrically symmetric system, so I like to draw them from a front view. So if you're looking at a toilet paper roll from the front, it looks like a circle. And then I also like to draw it from a side view. And if you look at a toilet paper roll from the side, it looks like a rectangle. Okay, just the outline of it looks like a rectangle. The shadow of it, if you will. So from the front view, we are going to have a line of charge in the middle. And then that line of charge is surrounded by, so think about the line of charge as like a string. And then that string is surrounded by a toilet paper roll. And this toilet paper roll is a conducting uncharged conductor. So we have a thick uncharged conductor that surrounds the line of charge. So again, think about it like a line with a toilet paper roll around it. And then that toilet paper roll is surrounded by an even bigger toilet paper roll, which is right here. Okay? Now, the radius of the inner wall of the conductor is A. The radius of the outer wall of the conductor is B. And the radius of the outermost toilet paper roll, if you will, is C. So now let's draw this from the side view. So side view, I'm going to take all of these and extend them like this. Like I'm doing a technical drawing. Okay, so the inner line just looks like a line seen from the side. The inner toilet paper roll is thick, so it goes from here to here. So there's the top of it. Here is the bottom of it. I need to get more pens. My pens are running out of ink. And then the outer toilet paper roll, here's the bottom and here's the top. So again, this looks like a string with a toilet paper roll around it, and then a bigger toilet paper roll around that. Okay, so this inner line of charge has a constant linear charge density of lambda 1. So that's a constant. And so just to remind you what linear charge density is, that is dq dx, charge per length. The outer one has a linear charge density that is negative lambda 2, okay? And it is also a constant. And we are given that lambda 2 is greater than lambda 1. So that the amount of negative charge is bigger than the amount of positive charge, okay? And so what we want to do is we want to figure out what's going on with the electric field. Okay. And so excuse me. So we have essentially 4 regions here. So our first region is R is less than A. So that would be in this space right here, in between the central line and the inner wall of the conductor. And then we have R between A and B. So that is inside the conductor. Then we have R's between B and C, which would be the electric field in the space between the outer wall of the conductor and the outer toilet paper roll. And then we have R is greater than C, where so that is going to be R greater than C is going to be completely outside of the outermost toilet paper roll. Okay? And so one of the things I like to do when I'm doing these problems is it's kind of nice to just do a table. And in the first column of the table, I put charge enclosed. And then in the other column of the table, I put the electric field. Okay? So if R is less than A, then that means that our Gaussian cylinder is kind of like this. Okay, so it's not big enough to pass into the conductor. Okay, and our Gaussian cylinder is always going to have some length L. Okay, so how much charge is this enclosing? Well, you can see that it's basically enclosing this segment of the central line of charge. Now that central segment, okay, has length L, and so because lambda is charge per length, if I take lambda and I multiply it by length, that's going to be the amount of charge that is captured by the Gaussian surface. So this one has charge enclosed of lambda 1 L. Okay, so I plug in, so then what I do is I plug in lambda 1 L for charge enclosed here. And what I see is that I have L in the numerator right here, and I have L in the denominator right here, so L cancels out. Right, the electric field shouldn't depend on the length of your Gaussian cylinder. Okay, and we get an electric field that is lambda 1 over 2 pi epsilon naught R. So I derived that result on the second lesson about Gauss's law. For the second region has our Gaussian surface inside the conductor. Okay, and as we know, inside the conductor, No calculation is necessary. You know that the electric field is 0. Okay? What if R is between B and C? So that means that our Gaussian cylinder extends into this region. Okay. Now, I guess I forgot to say this, but this is a neutral conductor. Okay. So that means that the conductor has no net charge. It will have some charge on its inner surface and its outer surface, but the amount of charges are equal and opposite because it's neutral. Okay. So making the Gaussian surface bigger now doesn't cause it to enclose any more charge because the conductor doesn't add anything to the charge enclosed. It is neutral. If it was not neutral, that would be a different story, but it is a neutral conductor. So what that means is that the charge enclosed will once again be lambda 1 L, and our electric field will once again be lambda 1 over 2 pi epsilon naught R. Okay? Now, what if our Gaussian surface was real big? Or real big enough to enclose all the toilet paper tubes? All right? So then it is not only enclosing the inner line of charge, but it's also enclosing the outer toilet paper roll of charge. Okay? Now this one has a charge per length as well, so we simply, again, multiply by the length, multiply lambda by the length to get the, total amount of charge enclosed in here. So that's going to be lambda 1 L minus lambda 2 L. All right. Again, the L's cancel out, and so we would get lambda 1 minus lambda 2 over 2 pi epsilon naught R. Okay. Now, because lambda 2 is greater than lambda 1, this is going to be a negative number, which means that the electric field will point inward. So it switches directions from going outward in this region to going inward out here because there's so much negative charge on this outer toilet paper roll. So what if we wanted to graph electric field as a function of R? Okay, we want to graph electric field as a function of R. I'm tired today. Somebody help me. So there are 3 important values. R equals A, R equals B, and R equals C. Okay? And I know that if R is between A and B, I get an electric field of 0, so I can immediately put that one in. For the other one, I can see I have a 1 over R dependence. 1 over R. So R is the variable on the horizontal axis, so I treat everything else like a constant, and I just zero in on R. So this is going to look like a graph of y equals a constant over x, right? Because electric field is like y, R is like x. So I have electric field is 1 over x. Now, if you've seen that graph before, you know that it comes down from infinity like so, like that, starts to level off. And, okay, but then once it hits A, it drops to 0. Then once we hit radius B, it resumes the exact same pattern that it was doing before, right? Because these two formulas are the same. So notice how I draw a dashed line here, and I just kind of continue the pattern, and then that pattern just picks right back up again where, not where it left off, but it just continues the pattern. okay, until we get to C. And then again, we get a 1 over x type graph, but now the constant is negative, so it's like going to look like negative 1 over x, which comes up from negative infinity. It kind of goes like that. So then now the graph is going to jump down and start coming up from negative infinity. So that's what our graph is going to look like. These always look like saws to me, like you're looking at a saw, the teeth on a saw. All right. So now we're going to talk about what if the charge, so these were all sort of like thin one-dimensional things, okay? But what if we have a bulky wire, for example, not a wire that's infinitesimally thin. It's a bulky wire. So we have something like you know, it's a thick charge distribution like that, something like that. Okay. And so in that case, you would be given a charge per volume, dq dv. And what if this is not a constant? So it's rho of r. Okay? So that is, and so what does r mean? R is the distance away from the axis of the distance away from the axis of the cylinder. So if we were looking at this point right here, let's say that's a point P, then R is going to be that distance. Okay, and then this would be a right angle. Okay, so that's what I mean by R. So it doesn't depend on if the point is over here. You know, if we go in a different direction, it only depends on distance from the axis of the cylinder. Okay? So what if that is not equal to a constant? Well, if we multiply both sides by dV, d volume, we get dq is rho dV. All right. So now the question is, well, what does dV mean? And if you had a spherical symmetry, then dV was 4 pi r squared dr. But because we don't have spherical symmetry, we have cylindrical symmetry, we have a different meaning for what dV is, okay? And so what you do is you just look at, you have a cylinder, the volume of a cylinder is pi r squared, okay, times its length. So if we want to know the volume of a cylinder, it's like a disk, a circular disk, which has an area of pi r squared extended along the length of the cylinder. So then we can take the derivative of this. So dV dr is equal to 2 pi r times L. Multiplying both sides by dr, we get that dV is equal to 2 pi r L dr. Okay. So we then take this and we plug it back into here, and we get that dq is equal to rho times 2 pi r L dr. And then if we want the total charge enclosed within the Gaussian surface, we need to integrate both sides. So the charge enclosed is going to be, and our integration variable is r. So 2 pi and L can be factored out because they don't depend on r. So I have 2 pi L times the integral of rho times r dr, and that goes from 0 to little r, where little r is the radius of the Gaussian surface. Okay, so it's this radius right here. Okay. Yes. I'm planning the problem that I'm about to do, and I just wanted to make sure I got it right. Okay, so basically how this works is we then take this integral for charge enclosed, and notice how it's a function of the upper limit. So the upper limit of integration is the variable here, so the charge enclosed is a function of little r. And then we then plug it into the equation for electric field, which is charge enclosed, which is now a function of little r, over 2 pi epsilon naught L little r. Okay? And I'll go even further, and because see how we have 2 pi L here and we have 2 pi L here, so those cancel out, and we just get 1 over epsilon naught times r times the integral from 0 to r of rho times big R d big R. All right? So that's nice. Okay, so we're going to be using this expression. What was the, so yeah, so you can compare that with the corresponding expression for spherical symmetry. So now let's do an example. What if we have our charge density as a function of big R, all right, is equal to a constant, which I will call B, times cosine of, pi r over 2a. And that is for big R less than a. All right. And then it is equal to 0 for r greater than a. Okay. So if we were to graph, what does this rho of r look like? What does rho as a function of big R look like? It looks like cosine, which kind of goes, but the question is, when does it go to 0? Well, if we plug in r equals a, we would get cosine of pi over 2, which is 0. Okay, so it looks like cosine starts out at a value b, because cosine of 0 is 1, and then that's multiplied by b. And then it goes to 0 in its cosine way. Never said that before. It goes to 0 in its cosine way, and it gets to 0 after an amount a. And then if big R is greater than a, it just stays at 0. So it just does that. All right. So let's go ahead and do this integral. So we're going to have two cases to consider. All right. The first case is if the radius of our Gaussian surface is less than a. And then the second case is if the radius of the Gaussian surface is greater than a. All right? So if it's less than a, our charge enclosed as a function of little r is 2 pi L times the integral from 0 to little r of b times cosine of, I meant to put a 1 over big R here. All right. My bad. So it actually doesn't look like this. Forget that. And you will see why in a second. Okay. The reason why is because this is 1 over R. Okay. Times cosine of pi R over 2a. Times r dr. So that's why I wanted the 1 over r there, because that 1 over r cancels out this one. And I can then factor out b as well, because b is not the integration variable. So I have 2 pi lb times the integral from 0 to little r of cosine of pi big R over 2a. All right, d big R. So the integral of cosine is sine, and then doing use substitution, or however you want to justify that to yourself, because the argument of cosine is not just r, it's r times a constant. We then have 2 pi lb times 2a over pi times sine of pi big R over 2a So this is the factor that comes from the chain rule, or the use substitution, and then evaluated from 0 to little r. So sine of 0 is 0. So the only term that matters is the little r term. So what I get is that the charge enclosed as a function of little r is 4 LBA sine of pi little r over 2a. So that is the charge enclosed as a function of little r. Okay, which I then plug in to this formula. Okay, and when I do that, I get Mr. Bugs. I get that the electric field is equal to charge enclosed 4 LBA sine of pi little r over 2a divided by 2 pi epsilon naught L r. So the L's cancel out. This cancels out and becomes a 2. So I get 2BA over pi epsilon naught r times sine of pi r over 2a. So that is the electric field as a function of r when r is less than a. Okay? Now, here's the thing. There is actually a maximum value to the charge enclosed. All right, so let me tell you why. The reason why is if this is your Gaussian surface or your Gaussian cylinder, if it's that big, it's enclosing the same amount of charge if it's that big or if it's that big or if it's that big. So as long, because see how the charge density drops to 0? So as long as we make the Gaussian surface bigger than the size of the charge distribution, it's always going to have all the charge, okay? So there's a maximum value to the charge enclosed, okay? So the charge enclosed, its maximum value, all right, as a function of r, is equal, or I guess that's not a function of r. What we're going to do is we are going to set little r equal to a. Why? Because that is the radius at which the charge density drops to 0. Okay? So it drops to 0 after that. So what I do is I plug little r equals, I plug a in for little r, and I get 4lba sine of pi over 2, and then I have a over a. All right, so that is just equal to sine of pi over 2, which is 1, and I get 4lba. All right, so then I can find my electric field as a function of r by plugging that back into this formula, and I get 4lba over 4 pi epsilon naught rl. The 4's cancel, the l's cancel, and I get ba over pi epsilon naught r. So this is the electric field when r is oops, this should be a 2. My bad. That should be a 2. So this is 2. This is for r greater than a. Okay. So yeah, so the integral part is fairly straightforward, but where it gets a little bit tricky is understanding the idea that there's a maximum charge enclosed if you have a finite distribution. So once the Gaussian surface encloses all of the charge distribution, making it bigger won't make it enclose any more charge. Okay? So that is my lesson for today, and I will see you in the Zoom room.